Alright, so today we're just going to do an application of the implicit function theorem. So first let's check that the assumptions hold. So we suspect that this f is going to be like our big X. And we suspect that because we notice that when we plug these points in, f is going to give us 0, which is very convenient. Okay, so let's check that the assumptions hold then. So f of x0, y0, u0, v0, that's equal to 1 plus 0 plus 1 plus 2 minus 4, 1 plus 0 plus 1 plus square root 2 minus 2 plus square root 2. That's equal to 0, 0. Also, we need to show that it's C1. So let's take the partials. F equals 2x, 2y, 2u, 2v, 1, 1, 1, 1. So we see that it's also C1 because all the partials exist and they are continuous. Now let's check that it's invertible in terms of the variables we're solving for. And we can tell what variables we're solving for by the partials. So because we're trying to find du, dx, dv, dy, we see that our ultimate end goal will be trying to solve for u and v in terms of x and y. And in order to do this, we just have to check that d, u, v, f is invertible. And what does this mean? So, in other words, we want the determinant d, u, f is not equal to 0. And that's easy. So this is du, v, f. And we see at 1, 2, that's just going to give us the determinant of 2 square root 2, 1, 1 equals 2 minus 2 square root 2, which is not 0. So both assumptions hold and we can apply the implicit function theorem. And what the implicit function theorem tells us is that there exists a function g such that g of u naught, again, we're trying to solve for u naught, v naught in terms of u and v in terms of x and y in a local neighborhood around this point. So we know g of x, y, x naught, y naught equals u naught, v naught. And secondly, f of x, y, u, v equals 0 for all x, y near x naught, y naught. That just tells us that the function is, so the points in this neighborhood are like on the function. And then finally, this is where we're going to be able to find our partials. We see that dg of u, v, x, y is, so this is how we're going to solve for du, dx, and dv, dy, is going to be equal to negative d u v. Again, we're solving for u and v in terms of x and y. Invert that times d x, y, f. Okay, and actually I shouldn't have erased the partials because that's actually going to help us. So we remember that df is equal to 2x, 2y, 2u, 2v, 1, 1, 1, 1. And this is our du, vf, aka what we're solving for. This is our dx, y, we want to solve uv in terms of. And we see that when we plug this in, so df 1, 0, 1 square root 2, that's equal to 2, 0, 2, 2 square root 2, 1, 1, 1, 1. This makes things a lot easier because we can just see that, again, this is our du, v, this is our dxy. So it's going to be equal to times 2, 0, 1, 1. And again, remember that in order to invert a matrix, you divide by the determinant, which is 2 minus 2 square root 2. and you negate the off diagonal and reverse the main diagonal. Reverse the main diagonal, negate the off diagonal, and you multiply. Just do some simple computation. Kind of running out of space here, so let me erase this. Okay, this, remember, is our dg u v in terms of x, y at our point 1, 0, 1, square root 2. Okay, so yeah, so this is going to be equal to 1 over 2 square root 2 minus 2 times 2 minus 2 square root 2 negative 2 square root 2. Is that right? Yeah, okay. 0 and 2. That's going to equal negative 1 and square root 2 over 1 minus square root 2, 0, 1 over square root 2 minus 1. And we see this is equal to du dx du dy dv dx dv dy. And thus du dx is equal to negative 1, dv dy is 1 over square root 2 minus 1. And we're done.